The next presentation is about steel jacketing, and it will be presented by Andreas Lampropoulos. For those that just connected, I'm just going to present Andreas Lampropoulos. He's a principal lecturer at the Civil Engineering Department of the University of Brighton in the UK. His main research agenda spans the areas of novel construction materials and seismic strengthening retrofitting of existing structures. So Andreas, welcome again. Whenever you're ready, we begin. Thank you.
Thank you very much, Eduardo, for the kind introduction. Hi, everyone again. Good morning to everyone. So I will continue now with the second presentation from our group. Actually, this is on the steel jacketing. The authors of this chapter are presented in the slide. Is Apostolidis, Dritsos, Yarlelis, Kyriakidis, Lampropoulos, Lima, Mateos, Mosele, and Repapis. And I will start now with the main part of the presentation, which is, as I said, on the steel jacketing. So this is the technique. We have some photos here. It's actually the casting of steel jackets and laminates. And the main applications where we should use this technique is when we actually need to enhance the ductility of the structures. So actually when we add the steel jackets, we enhance the mechanical characteristics of the concrete. We provide strength and strain capacity of the concrete are increased, leading to enhanced ductility. At the same time, this technique can be used to increase shear capacity. So this actually works as additional, this can work as additional shear links. And this can also be used to rectify insufficient lap splices. So in case of insufficient lap splice length, this could be used to enhance and rectify, resolve these issues through the confinement in this area. So these are the three main applications where we could use the steel jacket method. In addition to all those, we can use them also for temporary applications when we have severely damaged columns or structural elements, and when they have lost the capacity, we can temporarily use them in order to support the structures. Some of the main benefits of the technique is that it's quite simple. The construction process is, the construction industry is quite familiar, so the material is steel, we know how to use this. The construction process is quite simple too. This is considered mildly invasive, so we do not do significant damage to the existing elements. So we do not drill the initial columns and beams and so on. And an additional benefit is that the dimensions of these elements are not significantly increased. So we have very, very small increment of the dimensions through this technique. We have, the main technique is considered the steel cage technique. In this case, we have the steel angles which are connected to the steel strips. Any gaps due to the geometrical surface defects can be filled with non-shrinking cement, grout, or epoxy mortar. And we can also ensure a tight fit, either by pre-stressing, or we can have preheating of the steel strips prior to welding. So these are some techniques which could be used to ensure that our steel cage is well connected to the existing columns. You can see here also some examples where we have the steel strips which are connected to the angles, while we can have also a full steel plate which could also be used too. Another technique which is considered also steel jacketing is the epoxy bonded steel plate technique. So in this case, we don't have angles and laminates, but you have U-shaped overlapping steel plates. So there are not only angles and laminates, we have some U-shaped elements, and they are overlapping, and with the welding, we can ensure that this works as a jacket. And we should also use epoxy glue. In these cases, we should make sure that the thickness will not be big, so we should have a quite small thickness to prevent delamination and premature debonding. And thin elements, thin plates, normally prevent a better connection because actually they follow any surface anomaly. So when the surfaces are not really straight, these may also follow the pattern. They can follow the surface of the initial elements. Regarding the design procedure, as I said in the document, you can find detailed information about the design process, the construction process, any supporting documents required, and so on. Now I will focus on the design process, and I will briefly present the case study since there is quite limited time. And if you wish, you can go to the main document to find additional information about the technique. So for the design process, I will start with the axial strengthening. Ductility improving through confinement will follow, shear strengthening, and confinement of insufficient lap splices. Starting with the axial strengthening, so when we have steel cages, the contribution of steel cage is due to the fact that the steel cage leads to a confinement of the concrete, therefore the strength of the concrete is enhanced. In addition to this, there is a contribution of the external steel angles in this axial direction. While when we have epoxy bonded steel plates, the U-shaped ones that was presented before, in this case, we consider that the main contribution is due to the confinement effect. So when we have confined concrete, we know that the behavior is as you see here. So we have FC, the one here is the unconfined. Through the confinement, we can enhance both strength and strain capacities, right? So we know how we have the equations to calculate the enhancement of strength and the increment of strain capacity at the maximum and at the failure. So we have those equations, and depending on the amount of reinforcement that we use and the properties of the materials, we can calculate the enhanced strength and strain capacity. And for the strain capacity, we have different equations. This is a strain capacity at the ultimate. We have different equations for rectangular, for circular, and for triangular compression zone. Now, in addition to the effect of the confinement on the mechanical characteristics of concrete, we should also consider the confinement effectiveness coefficient alpha. So this practically represents how much of the volume of the concrete is affected by the confinement. So what is the beneficial effect of the confinement in terms of the volume of the concrete? And this is calculated as alpha S times alpha N, where alpha S is the effectiveness along the height, while alpha N is the effectiveness in plan. So practically, we have the ratio of the effective area over the total area for both plan and elevation. And from those ratios, we can then calculate alpha S and alpha N. So alpha S is the effective, the confined area over the total one along the height, and the same in plan. So we have the confined over the total one, and there are suitable models in the literature which gives us, as we see here, alpha S and alpha N. So by multiplying alpha S with alpha N, the effectiveness along the height and in the cross section, we can calculate the confinement effectiveness coefficient alpha, which, as I said, represents the volume of the confined concrete over the total one. In case of cross sections confined with circular strips, we have other similar equations proposed by Eurocode data. Now, when we go to calculate the ductility enhancement, which is one of the main targets for this technique, so it is quite common to want to enhance ductility. So we can calculate how much the ductility is increased in terms of section curvature. So we have the curvature at the failure over the yield. And this can be calculated using this equation that you see here, which is proposed in the Greek code for the strengthening. And this clearly depends on the amount of reinforcement we are adding. And actually, this is, in most cases, the target. So if we know how much is the target in terms of ductility, then we can go backwards and calculate how much is the target in terms of strain, and then we can go back and calculate how much is the amount of the reinforcement which need to be added in order to provide the required ductility. So for a given mi theta, we can calculate how much is the strain capacity and the strength of the concrete, and going back to these equations, we can calculate how much is the rho SW, which give us which can give us the amount of steel we need to add. Moving now to the shear strengthening. In this case, we know that the steel cage can significantly enhance the shear capacity of our existing elements, and we know the equation which can be used in order to calculate the enhancement of shear capacity is the one that you see here. Now, this depends on, this can be calculated if we know the jacket efficiency factor, which actually depends, is different for the steel cage, different for the epoxy bonded steel plate, is the lower end for the epoxy bonded steel plate, while for steel cage is a range between 0.4 and 1. It depends on the thickness of the steel strips, the width of the steel strips, the centerline spacing of steel strips, the depth of the concrete section, the yield strength of steel, of course, and the inclination of the compressive strut with respect to the elements. Actually, so this is the equation that can be applied to calculate the shear enhancement. This was proposed by Fardis 2009. And moving from the shear strength enhancement, we go to the lap splices area. We know that the steel cages can also be used to effectively confine the rectifying sufficient lap splices. So we have an example here which shows the lap splice area. So actually with the steel cage, we provide the confinement in the area of the lap splices, and we can calculate the amount of reinforcement we need in order to rectify the insufficient lap splice length. So AJ over S, which is the cross-sectional area AJ of the reinforcement of the steel cage. S is the spacing. Gamma is a safety factor, and I will explain later on the next. In case of epoxy bonded steel plates, the same equation can be applied by using where WJS and where this ratio we put the thickness. So this is the equation which can be used in both cases. Some other things which are required here is the coefficient lambda S, which is here in order to express the contribution of the available length. So we take into consideration that some of the load can be undertaken from the length of the overlap, which can be reduced or insufficient, but still can take some loads. But in order to do so, and in order to take into consideration the contribution of the available length, we know the code says that we should have at least 50% of the required stirrups. Otherwise, we do not take any contribution, and we should take that all the load should be taken by the external confinement. So if we have 50% of the required stirrups in this area, we can take into consideration the contribution of the existing length using this ratio, which is the length we have in place over the required one for new structures as proposed by the codes. So that's how we calculate lambda S, and this can be used here in order to calculate the required reinforcement. Of course, a simplified approximation is to take this as 0 and consider that the jacket will take the whole, then the confinement will be used to undertake the full load. Now, some additional factors which are required is this factor beta that you see here, which correlates the compressive strength, introducing the concrete with the tensile strength of the confinement material, which is different values for corner bars and bars not in the corners. We have also the friction coefficient at the surface of the potential slip location of the anticipated cracking. So when we are expecting cracking in the area of the lap splices, this μ is representing the friction in the cracked surface. And the sigma JD is actually the stress, the confining stress, and actually how much is the contribution we are getting is a Young's modulus of the material times the strain. Regarding the strain of the material, in the absence of more details, we use this equation here, which depends on the width of the crack, which can be calculated depending on the relative slip, which is given for the different performance levels. So we know that depending on the performance level we need to design, we have different limits for the slip at the crack at the lap splice area. From the slip, we calculate the width of the crack, and from the width, we calculate the strain, which then fits in the equation for the stress, and we calculate the sigma JD, which is the stress contribution of the confining material. And of course, we have the material properties and the cross-sectional area. So these are the main parts of the design procedure that you will find in the document in addition to all the sections for the execution process, supporting documents, and so on. And we have also included 2 case studies. So there is one case study of the school that I presented before in my first presentation on the frame encasement. So we had the same structure which was examined before with shear walls. Now we are using steel jackets. So this is a school in Kefalonia, as I said. The designer was Equidas Consulting Engineers. As I mentioned before, the structure was not hit by any, it was not severely damaged by the earthquakes, but it was decided that needs to be strengthened due to the educational, due to the fact that it has a high importance as an educational building. And now, before actually we're using frame encasement, now we examine steel cages. We have all the calculations are included in the documents, and I have here just some details about the steel jacketing, which is the solution for considering significant damage level and the target curvature ductility equal to 10. And there is also a second case study on another building in Argentina. So there are details about another structure which had some quite serious design defects and construction defects and some damages. And you will find detailed information about the application and the construction of the steel jacketing method. And this brings me to the end of my presentation. I would like to thank you all for your attention. And again, I would like to acknowledge the significant contribution of the reviewers. As you see here, Alessio Casaldi, Constantin Hagliori, Sylvain Satangnar, Hugo Corres Peretti, Freddy Fernandez, Ricardo Marin, Alberto Martin Calan, Victorio Hernandez Balat, Kypros Pilakoutas, Tamon Ueda, and Tatila Vardem. Thank you once again.
Thank you, Andreas, for this very interesting presentation.